Welcome to Part 2 of Lecture 10 for Chemistry 312, Radiation Reactions. This lecture is on dosimetry and hot atom chemistry. The readings for Part 2 are the same as Part 1. Modern Nuclear Chemistry, Chapters 16 and 17. Nuclear and Radiochemistry, Chapter 6 and Chapters 11C. In the first part, we discussed the interaction of radiation with matter. We explored the role of neutrons, positive ions, electrons, and photons, similarities and differences on their interactions of radiation with matter. In this lecture, we're going to focus on dosimetry, how we can quantify that interaction of radiation with matter, how we can use that understanding in radiation protection, and then we're going to end this lecture with a discussion on hot atom chemistry, where a nuclear reaction occurs and that nuclear reaction induces a chemical reaction, which is the first step in a chemical process. One effect of all these interactions of radiation with matter, when it comes to radiation safety, is to try to quantify the influence of a certain radiation field on radiolysis and eventually health concerns. This is the area of dosimetry, where you try to get a relationship between a measurement in a radiation field and a chemical or biological change. There should be some sort of effect of dose on a chemical or biological change, and dosimetry is a way to try to quantify this relationship. As we discussed, when these particles interact with matter, they cause ionized molecules, secondary electrons, etc. And these in turn drive chemical or biological changes. So when we talk about absorbed dose, we talk about the energy absorbed per unit mass of any target for any kind of ionizing radiation. So when we talk about absorbed dose, we talk about units such as gray or rad. We're talking about the energy absorbed, and we're not really focusing on the ionizing particle that's depositing that energy. The gray is 1 joule per kilogram. In the United States, we use the rad, where the rad is 100 ergs per gram, and it works out that 1 gray is equal to 100 rad. So for radiation dose units, we're going to have this 2 orders of magnitude difference between, say, SI units and what we use in the United States. This absorbed dose, so a gray or a rad, is often referred to as dose, and it's treated as a point function. So it has a value at every position in an irradiated object. The important thing to remember about these terms is the relationship between the SI unit and the US unit. So in this case, a gray and a rad, the difference is 2 orders of magnitude. So 1 gray is 100 rad. The dose equivalent is basically taking this absorbed dose that we talked about and normalizing it to different types of radiation. As we saw that charged particles, electrons, and photons behave differently with matter, and this influence should be described somehow when it comes to this biological effect. The difference is really driven by this linear energy transfer, and we're going to call this dose equivalence and to try to compensate for this, where the dose equivalence will be equal to the dose d times q, and q is some dimensionless value. There's a number of reports out in which define what this value should be. It's often a function of the particle and the energy. Q can vary from 1 to 20. There's some information about what Q should actually be from NCRP report that's listed here, National Council on Radiation Protection. The data that's shown here defines the Q as a function of the type of radiation. So photons, X and gamma rays, have a quality factor of 1. So what we would see for the gray would be the unit for the sievert, the rad for the rem. Electrons and positrons are 1. Neutrons are somewhat dependent upon the energy. Protons and alpha particles vary from 1 to 20. For conservative measurements, we'll just use 20 for alpha particles. So simply put, for the work that we'll focus on, we'll use 1 for photons, 1 for electrons, and alpha particles we'll use 20 to convert from a dose to dose equivalent. So when the dose is in gray, the dose equivalent is in sievert. When dose is in rad, the dose equivalent is in rem. Again, as we mentioned before, 1 gray is 100 rad, so 1 sievert is 100 rem. The biological distribution of an isotope can also be an important consideration when one evaluates internal dosimetry. And here are some examples of distribution of certain radionuclides. For instance, thyroids is a known collecting point for iodine. Calcium in the bone will mean that divalent metal ions such as strontium and radium go to the bone. Complexes, so metal ligand complex, when it goes through the kidney, there's a pH change, there's a decrease in pH. So complexes can be released, so metal ions can be released at these lower pHs. So these will have different effects on different parts of the body. So this is all related to internal dosimetry. And there's models, again, from the National Council on Radiation Protection that have models about different radionuclides and how they behave in the body. And it's also, as we'll see when we talk about annual limits on intake, a reason that radionuclides differ from one another. Right. Here's some data on some typical radiation levels. Typical background radiation, this is an updated value, is around 6.24 millisieverts per year for typical US public. That would be 624 millirem per year, again 2 orders of magnitude. And then here's some other data for consideration. If you look at the annual background of about 6 millisieverts per year, temporary short-term dose of 1,000 millisieverts causes radiation sickness. 5,000 millisieverts, 5 sieverts, short-term dose would be an LD50 for a month. And 10,000 millisieverts, 10 sieverts, as a short-term dose would be fatal. And this is a method for determining relative intensities of different radiation doses. One can perform dose calculations knowing information related to the average particle energy and its activity. If one wants to use the dose in grays per second, this equation here transforms to a very simple equation where you get 1.6 times 10 to the minus 10, A, which is the concentration in becquerels per gram, times E, which is the average energy. This equation is for alpha and beta. For alpha, the average energy can be the energy of the decay, whereas beta, since we have a range of activities, we actually use 1/3 of the beta max as the average energy. So we can show how this would work. Imagine a calculated dose of 1.2 times 10 to the 5th becquerels of carbon-14 and 50 grams of tissue. Beta max for carbon-14 is listed here, 0.15 MeV. The average energy is 1/3 of that, so about 0.052 MeV. Plugging these values into the equation, A is equal to the activity divided by 50 grams. We have our average energy listed here. Plug this into the equation. We get a value of 20 nanogray per second. Doesn't sound like a lot. The question is, how can we compare what this value is so we get an idea of whether or not that's actually a high or low dose? Well, if we compare it to the average background, we stated that the average background is 6.24 millisieverts per year. That winds up being about 2 times 10 to the minus 10 sieverts per second, or 0.2 nanosieverts per year. So this calculated dose is 2 orders of magnitude larger than the background dose. So this 20 nanosieverts per year is 100 times background. So that's a reasonable estimation, a value that one can use to compare a calculated dose with a meaningful value. We can use a different equation for calculating dose from photons. The equation is listed here, and it contains different terms. One is air absorption coefficient, mu divided by rho, shown here. This is a coefficient that describes the absorption of photons by air, and the values listed here. This is generally consistent from 60 keV to 2 MeV. So for most photons that would be released from radioactive isotopes, this value can be utilized. We can take our dose term here, we can rearrange it into grays per second as we did for beta and alpha particles, and we get a value that says, is shown here, 3.44 times 10 to the minus 17 C, which is our activity in becquerel, times E in MeV, divided by R squared, where R is a distance in meters. And remember, we also need to normalize our gamma energy to the yield of photons. So when we take C in becquerel, unless the photon yield is 100%, we need to take that into consideration. So as an example, let's consider a case where we have 10,000 becquerel of sulfur 38 that's at 0.1 meters. We know that if we look up 95% of there's 95% gamma yield for a 1.88 MeV photon. So we could take these values and substitute it into our equation that's shown here. So D is equal to our constant, and we multiply that by the activity. So it's 10,000 becquerel. Then we need the energy, which is 1.88 MeV, and then we add the 0.95 to represent the 95% gamma yield, and we divide that by 0.1 squared, the radius, the distance in meters, and we get a dose of 6 times 10 to the minus 10 grays per second. Once you have the dose, you should be able to use that information to evaluate some detriment due to the exposure from that dose. An example of that is provided here, where you could talk about some detriment, some sort of cancer, non-fatal cancer, genetic effects. And this is parceled out for either adult workers or the population as a whole. You can think about those as different potential sets of exposed people. You can use this to evaluate what would be the detriment from a given exposure. So for instance, what is the probability of detriment for a 2 millisievert per year for 10 years to an adult worker? If we have 2 millisieverts per year times 10 years times 5.6 times 10 to the minus 2 detriment per sievert, which is given from this value, we get this value, which is basically the increased risk of having some detriment. If we look at the maximum occupational dose for 30 years, which is 50 times 10 to the minus 3 sieverts per year, we do that for 30 years, we see that the increased probability of having some detriment is 8.4%. One of the reasons that we can only evaluate this detriment as a probability has to do with the actual biological effects due to radiation exposure. As we see here, there's a table of events that can occur over a function of time due to biological interaction with radiation. The time components here go from very short, 10 to the minus 18 seconds, to generations. Those effects, which are associated with health, cellular processes, tissue damage, clinical effects, are extremely long-term events compared to the chemical and physical nature of the interaction of biological material with radiation. Therefore, it's very difficult to quantify. However, the theory of a linear dose effect says that any amount of radiation above background is harmful, and information on that can be seen from this website. Whether or not the linear dose effect is real and how low-level radiation affects health is not clear, but the model is this linear dose effect. Based upon allowed limits, one can start to explore the limits for given radionuclides based upon their decay and biological behavior. This information is available from this NRC website. You can go here and find out the occupational value limits for any radionuclide, including the ones that we work with. There's two data sets one needs to evaluate. The annual limits on intake is derived based upon a dose received of 0.05 sievert from a given radionuclide. The ALIs, as they're called, the annual limit on intake, is listed here. You see that there's two different ones, an oral ingestion or an inhalation. This gives you the limits on what would be the activity in microcuries for oral ingestion, in this case for americium-241. And here's the inhalation for americium-241. And you see that the differences are extremely large. The limit on intake for inhalation is usually much lower than the oral ingestion. Another unit is the derived air concentration, the DAC, and this comes from the annual limit on intake. And it's the assumption that there's a certain radionuclide in the air, and it's based upon the ALI, so the annual limit on intake, assuming that you would be breathing this air for 2,000 hours, that would be a typical work hour, and that your exchange of air is listed here as 2 times 10 to the 4th milliliters per minute. And as you can see, your derived air concentration are extremely small values, and they're listed in microcurie per milliliter. The values are shown here, and you can go to this website and get all this information for any radionuclide. The information that we just discussed on ALIs and DACs, so the annual limit of intake and derived air concentrations, are the basis for activity levels in radiochemistry laboratories. I'm going to provide an example for the radiochemistry laboratory at the University of Nevada, Las Vegas, where the activity levels for certain isotopes are provided, and these activity levels are based upon the annual limit of intake and derived air concentrations. This information is used to describe a rad safety level for experiments. So for instance, if all the isotopes that one is working with has a annual limit of intake for ingestion of 0.01 or less of an ALI, that's at a rad safety level 1. Very basic work. Wide variety of people can work with this. If the annual limit of intake, the activity for the isotopes one working with approaches 1 ALI, then the rad worker level is 2, or an airborne ALI of 0.1, the rad worker level is 2. This means that the rad worker, for the researcher, needs a little bit longer skills, a little bit more supervision in working with activity. Rad level 3, we can go well above an ALI. It's broken into airborne or non-airborne. And there's also a component that says if we're using airborne or non-airborne, we have certain requirements such as using a fume hood or a negative pressure glove box. And then for rad level 4, the levels are even higher. Again, there's requirements on using negative pressure glove boxes above certain alley limits, and also interactions with the authorized user. So all this data is available, and one can use it to determine the risk levels or rad safety level for the experiment one is interested in performing. Data is also shown here for radionuclides that we frequently work with, the alley ingestion level, alley inhalation level, and then the rad levels associated with a given activity. And the activity is listed in microcuries. And you can have rad safety 1, 2, 3, whether it's airborne or not, and rad level 4, whether it's airborne or not. And again, radionuclides are listed from americium to zirconium. All this data is available, and you could use this data to calculate the necessary radiation level that you would be working with in the laboratory. An example of that is provided here. Assume that you wanted to do a level 2 for uranium-238. This is non-airborne. This is basically 1 alley. So if we go to the tables, we see that uranium-238, rad level 2, that's 10 microcuries as our limit. So the question would be, what would 10 microcuries, what mass of uranium is that equivalent to? Well, if we use activity equals lambda n, we find n, we can get moles, and then we can get mass. So if I take 10 microcuries, I then take 10 microcuries, I convert that to becquerel, I get my decay constant for uranium-238. I solve this equation. I see that 10 microcuries is 7.6 times 10 to the 22 atoms of uranium-238. That is 0.126 moles, and that winds up being about 30 grams of uranium-238. So this says non-airborne uranium-238. So if I had 30 grams of uranium-238 in solution, I would be at 1 alley. So I could work with this on the benchtop. What would be uranium level 3, non-airborne? If I look at the table here, I see that that is 500 microcuries. So I redo my calculation from 10 microcuries to 500 microcuries. I'm increasing that by 50 times. I need to do this in a fume hood, but now I can work with 1,500 grams of uranium. We can perform the same sort of calculation for technetium. Here's the data for technetium-99. Let's say what's the value for level 3 technetium experiment, non-airborne. I look at my table. I see that the value is 50,000 curies. And if you look at the data, it's either going to be the limit based upon the alley or up to 50,000. So technetium hits that limit. One of the reasons that the alley limit is so high is also coupled with the biological behavior of technetium. Pertechnetate ingested is readily passed, which is one reason that it's used in radiopharmaceuticals. So we can see that we have a value of 50,000 microcuries. We run our calculation. We convert that to becquerel. We use the decay constant for technetium-99. We get 1.8 times 10 to the 22 atoms, so many moles, and it actually works out to be about 3 grams of technetium. So we can work with up to 3 grams of technetium in non-airborne condition in our hoods. final topic of this lecture is on hot atom chemistry. These are the chemical processes that occur when a nuclear reaction unfolds in an isotope. This nuclear reaction can either occur through radioactive decay or through an impinging particle. This is also called the Shillard-Chalmers process. An example of hot atom chemistry is the activation of iodine and extraction of that activated iodine from water and ethyl iodide. In this case, ethyl iodide can be irradiated in a nuclear reactor. The iodine-127, the stable isotope, remains as part of the ethyl iodide. When that iodide captures a neutron and becomes iodine-128, it separates from the ethyl iodide and can be precipitated as silver iodide. In this route, only the activated iodine is separated. And this is due to the fact that the interaction with a neutron causes a chemical reaction. So that is described here. The iodine gets extracted into an aqueous phase from this organic and then precipitated. In order for this hot atom chemistry to occur, the reaction needs to overcome bond energy. Neutrons normally don't provide sufficient recoil energy. However, from a nuclear reaction you can get gamma decay. The recoil energy from the gamma decay can be calculated here with this equation. And if we look here at the table that's taken from nuclear and radiochemistry, we get the recoil energies in electron volts imparted to nuclei by different gamma energies for different masses. And remembering that we don't need that much energy, depending upon the gamma energy, to achieve a breaking of a chemical bond, since chemical bonds are only on the order of tens of electron volts. The mechanism that occurs in hot atom chemistry is that these bonds, chemical bonds, are broken due to the reaction energy. Certain conditions need to be met. Only the bonds of the produced atom must be broken. In the case that we discussed earlier with the iodine, if the bonds broke both the inactive and active iodine, the separation wouldn't be very useful. And then once the bonds are broken, they shouldn't recombine with fragments, and there should not be exchange with the target molecule. The kinetics of exchange should be slow. So again, with the example with the iodine, the produced iodine-128 should not exchange with the iodine-127 on the alcohol. And there should be a reasonable route to separate the new species. Halogens have been produced with this method, as one we described on the previous page, and these isotopes listed here have been produced. Beta reactions can also be exploited in hot atom chemistry. In this case, you're just looking at recoil, and often in recoil energy, bonds aren't broken because the energy gets distributed. However, internal conversion can potentially set the atoms into an excited state, and one can utilize this rearrangement of electrons to drive chemical reactions that can be exploited to achieve the separations. And again, looking at some recoil energies expected from various decay events are listed here. As we see, beta decay, positron decay, and fission certainly has sufficient energy to achieve separations. So in this lecture, part one, we focused primarily on the interaction of radiation with matter. We discussed and explored the differences of neutrons, positive ions, negative ions, and photons, their interactions of radiation with matter. We showed that there are differences, but we also talked about some similarities, primarily the formation of ion pairs and how those ion pairs lead to reactions with the material that those particles travel through. Those reactions are the basis of dosimetry, where one wants to measure the amount of energy deposited per unit mass and understand ultimately an effect that that deposition of energy provides. We talked about calculations for dosimetry. We talked about dosimetry units, Gray's sieverts, rads, and rems. We discussed a little bit about the limitation of dosimetry, particularly when it's coupled with models. We explored the influence of particles, particularly when we go from dose to absorbed dose. So the rad to the rem, the gray to the sievert, how an alpha particle has a much larger influence due to the fact that it has a much higher deposition of energy in a shorter range, so a higher linear energy transfer. And then we also explored a little bit about the measurements related to dosimetry. We used the information related to dosimetry to talk about annual limits on intake from radiation safety and how that can be used to derive and understand limitations of laboratory practice. And finally, our last component of the lecture was on hot atom chemistry, where we discussed nuclear reactions influencing the chemistry and how we could actually use this initial nuclear reaction to separate an unreacted isotope from a reacted isotope. So ideally, you could take a target that has not been reacted and separate it from the reaction product. Even though it's the same element, it's a different isotope. And the reason you can do that is that the chemical reaction drives the changes in the chemistry, and you exploit those changes to achieve a separation. Some questions that you may see or should be able to answer from Lecture 10 are provided here. What are the commonalities of interactions of charged particles with matter? At high energy, the loss is primarily through electronic excitation and material ionization. At velocities where they're slower and they're comparable to the K shell electron, ions begin to pick up electrons. So if you have a barrier charged particle going through a material, it starts to pick up electrons as it slows down. And at velocities compared to the valence electrons, elastic collisions dominate. And how do neutrons interact with matter? Well, they are primarily confined to nuclear effect. There's little electronic interaction for neutrons. So you have N gamma, N proton, N alpha, for instance, as the basis of interactions and detections. So if one wants to make a neutron detector, one wants to use a material that has a high neutron interaction, in which that can then be observed through the interaction of that material. Another question you should be able to evaluate: what's the most likely route for the interaction of 1 MeV photon with iron? And if you're given data that look like this is some sort of cross-section as a function of energy for different photon interactions. We know that there's a photoelectric effect, Compton absorption, Compton effect, and pair production. We see that here's the total, the black line, this blue, the photoelectric, is at lower energy. As the energy increases, Compton starts to dominate, and then pair production begins when you have enough energy to make a positron-electron pair, so over 1 MeV. So we know instantly that this is 1 MeV, we're not going to see pair production. And if we look at where this occurs, the dominant area is Compton scattering for iron. This is again data for iron. Other questions you should be able to answer have to do with utilization of stopping power. Remember, we looked at stopping power for protons through the P star, electrons through the E star data. Here we're going to look at some alpha particles through the program A star. Use the total stopping power that's available from this site. Again, for the other systems, the proton and electron also use total stopping power. So, for example, consider the interaction of a 5 MeV alpha particle with 1 micron layer of aluminum. So again, we want to utilize the equation to determine what's the energy loss. So the energy loss is stopping power times the thickness times the density. And the information available for aluminum, the stopping power for 5 MeV alpha in aluminum. If we go to the A star web page and we look at the data for 5 MeV, we get 6 times 10 to the 2 MeV centimeter squared per gram, and the density of aluminum is 2.7 grams per centimeter cubed. Plugging this into the equation, stopping power here, density here, and a thickness, well, we said 1 micron, so 10 to the minus 4 centimeters. We get an energy loss of a little over 0.1 MeV. So 0.163 MeV is the energy loss from a 5 MeV alpha particle as it traverses 1 micron of aluminum. Now, using the same database, we can actually investigate some more complicated systems. And here's an example of, as opposed to just using aluminum, what if we had an alloy of aluminum and molybdenum, where it's 50% by mass molybdenum? We could again go to the A-star web page, get the relevant molybdenum data. The stopping power is 3.68 times 10 to the 2 MeV centimeter squared per gram. The density of molybdenum much larger than the density of molybdenum is much larger than the density of aluminum, 10.22 versus 2.7. And we basically need to make a linear combination of the equations where since we're at 50% mass, we have to take the same equations except multiplying it by its relative mass. So 50%, we could basically say it's 50% dense molybdenum and 50% dense aluminum. So in this case, the equation has two parts. There's an aluminum part, which is the same as up here, except now we've taken half of it because we're basically saying it's half of the aluminum density. And then we add to that a molybdenum component. Again, it's the same thickness, but we say half of that density is due to molybdenum. And what we see is that now we have we absorb about 0.27 MeV of energy from this 5 MeV alpha particle in a 1 micron thick layer of this alloy. And if we go to 100% molybdenum, we just basically take this component of the equation, make this 100%, and we see that the energy absorbed is 0.376 MeV. And this is a very good comparison between shielding of material. Molybdenum is on the order of 2.5 times of the aluminum. So molybdenum, higher Z, denser material, more electrons, is better shielding than aluminum. Some other questions you should be able to answer. Relationships between derived air concentrations and alleys are shown here. So in other words, if I have an annual limit on intake, I can use this equation to determine the derived air concentration, or I can actually look up the values at this website. So if you were to ask to compare the derived air concentration for plutonium and cesium isotopes, you'd be able to figure out which ones have more stringent limits. You can also say, well, probably the plutonium, it's an alpha emitter for air concentrations. Also, since the alpha particle has a quality factor of 20 compared to a beta or a gamma from cesium. You can also use the derived air concentration to evaluate experimental limits for americium-241 as an example. Since you can, from the derived air concentration, you can get the annual limit on intake and the experimental level that one is allowed to work with, 1, 2, 3, or 4 as an example that we used for radiochemistry laboratory, is based upon the alleys. One could also perform a dose calculation. If, for instance, if there was a 1 milligram internal exposure of polonium-210, the absorbed dose is shown here from this equation. We have a constant where we have the concentration in becquerels per gram times some sort of average energy. For this work, we could talk about the absorbed dose. You'd have to put in a mass that it would be absorbed to. If you're using something like a reference person, that could be on the order of 70 kilos. Milligram, you'd have to concentrate this to activity. So I'd get becquerels in 70 kilos. So I get becquerel per gram, assuming a complete overall exposure. The average energy, you could look up for the average energy for the decay of polonium-210, and then you'd get this value in grays per second. If I want to convert it to sieverts, I need to multiply it by the quality factor 4 and alpha, which polonium-210 is. You can also do an equation where, for instance, calculate the dose from so many becquerels of americium-241 at a given distance. Here, one would just take this equation where the activity C is in becquerel, the energy is in MeV, so you need to get the gamma energy of americium and MeV. It's about 60 keV, so you need to convert that. R is in meters, and the data is shown here in meters, so divided by R squared. Also, the gamma activity, here's the total activity of the americium decay. You need to normalize it to the percentage that decays through gamma. And if you look up americium-241, it's about 37% of the time. When it decays, there will be an associated gamma ray. So you'd have to take this activity multiplied by 0.37 in order to get the activity that's due to the gamma. So you can use that to determine the dose. And finally, when we discussed hot atom chemistry, what are some of the principles of hot atom chemistry? When one uses a nuclear reaction for bond breaking to try to do separations for carrier-free isotopes. Well, one, when the nuclear reaction occurs on the molecule, that atom that absorbed the nuclear component that has a reaction product, for instance N-gamma, that new isotope that's produced should have its bond broken with the molecule that it was bound with. The fragments that are formed should not recombine. The released isotope should not exchange with the target molecule, so there should be slow kinetics, and the new species should be able to be separated. And again, alcohols of iodine were used as an example of this. When you've completed this lecture, please comment on the blog and respond to PDF Quiz 10.